Hi, welcome to part 6 of the video series about laws of motion. In the previous video, we have stated the third law of motion, solved some of its applications, and had a look at some multiple choice questions related to the third law of motion. In this video, we are going to learn about the universal law of gravity and how it is related to the difference of the mass and weight of an object. One of the fundamental forces which has been involved in the creation of the universe is the force of gravity. It is maybe the weakest of all the fundamental forces, but it has played a crucial role in the creation of the universe. According to the universal law of gravity, each body in the universe attracts every other body with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. Let's assume two objects of masses m1 and m2 respectively. Let's consider r as the distance between the centers of these two objects. Universal law of gravity states that the object with the mass m1 will attract the object of mass m2 with a force of F1 on 2. At the same time, the second object m2 will attract the first object m1 with a force of F2 on 1. These two forces are making together action-reaction pair. As we recall from the third law of motion, these two forces are equal in magnitude but opposite in direction. We can calculate these two forces by using the formula on the screen. As we can see, forces are directly proportional with the product of the masses and inversely proportional to the square of the distance between their centers. In the formula, we have one extra parameter or proportionality constant, uppercase G. G is the universal gravitational constant. Its value is same across all the universe and is equal to 6,67 times 10 power to minus 11 Newton meter square per kilogram square. Please don't confuse this big G with the smaller one, which is gravitational acceleration. According to the universal law of gravity, all objects in the universe are attracting each other. What about the objects in our room? According to our observations, some objects can remain in our room for years, but we have never observed them coming closer even by inches. Does it mean that universal law of gravity is wrong? To understand what is going on, let's see the formula in action. We are asked to calculate the force of gravity exerted by the object on the left on the object on the right. Both objects have mass of 1 kg and the distance between their centers is 1 meters. First, we write down the formula to calculate the force of gravity. Then, we substitute the values in the formula. G is 6,67 times 10 power to minus 11. Mass of each object is 1 kg and the distance r is also equal to 1 meters. As a result, force of gravity is equal to 6,67 times 10 power to minus 11. If we write it as a decimal number, we get the value on the screen. This is such a small number that even if there was no friction force preventing these objects from moving, it could take them millions of years to move a tiny distance. Force of gravity becomes more relevant if at least one of the objects has a huge mass. We can feel the effects of it on the objects on the surface of a planet. Any object we drop from a certain height is falling down. This is due to the gravitational force applied on this object by the planet. In an image on the screen, we have an object of mass small m on the surface of the planet with a mass of big M and radius of big R. By convention, if we have two objects with one of them with much greater mass than the other one, instead of using m1 and m2, we use big M for the mass of the heavier object and small m for the mass of the lighter object. Another convention is to use uppercase R for the radius of a planet. As the radius of the object is negligible compared to the radius of the planet, we can say that distance between the centers of the planet and object is equal to the radius of the planet. In this case, we can formulate the force of gravity as seen on the screen. Now, let's consider the following case. The object, which is initially on the surface of the planet, is now moving away from it to a significant height h. This time, the distance between the center of the planet and the object is not equal to the radius of the planet anymore. It is equal to the radius plus h, the height of the object above the surface of the planet. In this case, we have to adjust the denominator in the formula. There is too much information here and we need some examples to digest it. Including examples will make this video too long. That's why we will solve examples in the next video. For now, let's conclude this video by learning about the difference of the mass and weight of an object. In the video about the first law of motion, we have already learned that the mass is the quantity of a matter in a physical body, or it is the measurement of an inertia. On the other hand, weight is the force of gravity experienced by a body. Previously, we have learned that weight is equal to the product of the mass of an object and gravitational acceleration. Also, as you know, force of gravity can be calculated by using the formula on the right side of the equation. Each side of the equation has the mass of the object in it, which is represented by smaller m. We can get formula to calculate gravitational acceleration by cancelling small m in each of these two formulas. Gravitational acceleration is the acceleration of an object in free fall within a vacuum. In all our previous calculations, we were using 9.8 meters per second square as a value of g. But according to this formula, we can see that g actually is not a constant. It may vary depending on the values of the mass of the planet and its radius. It brings us to the conclusion that weight of an object is also not a constant, as it depends on gravitational acceleration. Our mass is the same wherever we are, because the amount of the stuff we are made of doesn't change. Our weight depends on how strong a gravitational force is acting on us at that moment. On the table, we can see the comparison of the weights of the same object of mass 10 kg on different planets. The average gravitational acceleration on Earth is 9.8 meters per second square, and the weight is 98 newtons. We say average gravitational acceleration because even on the surface of the Earth, g is not constant. For example, it has greater value on the poles and smaller value on the equator. On Venus, weight of an object is slightly smaller than the one on Earth, 89 newtons, as the gravitational acceleration on it is 8.9 meters per second square. The object will be heaviest on Jupiter, as the gravitational acceleration on it is 23.1 meters per second square, and the weight is 231 newtons. To summarize, in this video, we have stated the universal law of gravity. Then, we have learned how to calculate gravitational force applied on an object while it is on the surface of a planet and when it is at a certain height from the surface. At the end, we have discussed the difference of mass and weight of an object. In the next video, we will solve some examples to practice the knowledge we have gained in this video. Don't forget to subscribe and turn on the notifications in order to be updated about my new videos.